Our next speaker is Antoine Tilloy, and he will talk about linear feedback of continuous quantum measurements.
Okay, so thank you, Michel. So I'd like to thank the organizer for this very nice conference. I'm really humbled to be among such nice speakers. I hope I will not drag the level down too much. So my objective today is to talk about linear feedback of continuous quantum measurement in a slightly more general context than the standard Markovian case. And okay, so let's to extend the standard case we have heard perhaps the previous day and this morning. So just I would like to say first that this is a quite preliminary work. I had to fit within the subject of the conference, and unfortunately my earlier work is not that close, so it turned out that the very recent work was closer. So I have no nice paper to show for it right now. All of it is in the slides. It's the result of a collaboration with Lajos György in Budapest, and I mean a very large fraction of this work was done with him. And I also discussed quite a lot with Luca Ferialdi in Ljubljana, who is a real expert in non-Markovianity, and Pierre on this very problem of feedback. So I know he's trying to approach this problem in a slightly different way. So mine is probably, I don't know, more brutal, as you'll see, and maybe we can discuss in the end if it's smarter or not. Okay, so the first thing is what do we mean by feedback? Okay, in that case, I really mean the very naive thing. So you have a quantum system that is measured, I mean weakly or not, and the Hamiltonian depends on past measurements in a simple or a very complicated way. So you have this something that you probe your system, you measure, and you back react on it based on those measurements. So I'm probably the first person to loot this picture, and I'm probably not the last. So this is really analogous to what you have in the Harosh experiment, where you send Rydberg atoms to probe a cavity, and based on those measurement results, you can back react and act based on those measurement results. A nice way to also define what is measurement-based feedback is to see what it is not. So although there is also the name feedback, the concept of coherent feedback is slightly different. So you send quantum probes to your quantum system, but then the controller itself is also quantum. So it's slightly different from this setup where I can really, if you wish, write the measurement results on a piece of paper and back react based on them. Okay. Okay, so I will only focus on the non-Markovian, on extending what is known about feedback in those cases, but I will not consider this case, although I know people are trying to do the same thing, that is extend to control feedback that are not Markovian. So why are we interested in quantum feedback? And there are a bunch of tasks that you can do much more efficiently if the action you make on the system is depend on the measurement you did. So there are many papers who show how you can purify much faster your states. I mean, this was also seen this morning. There are schemes allowing you to also measure faster, to prepare states, to stabilize them faster, to correct errors in that, just the talk before, but you can also continuously correct errors. So that's the first motivation to talk about feedback, which is probably the closest to the subject of this conference. But there is also another way that I find feedback interesting, is that I just like to mention briefly. It will not be the subject of this talk, but it's very interesting because it allows to construct fundamentally hybrid quantum classical dynamics. So this is completely outside of this. If you try to construct new theories in which you have classical variables and quantum variables that are coupled, a nice way to obtain a theory that works by design is to use feedback. Because what is feedback if not the joint evolution of a classical controller and a quantum system? So if you want to couple classical and quantum systems, a good way is to write this evolution as a general feedback scheme, in which case you know that by design the thing will be consistent. And for example, you can try to do that with gravity. Okay, in the Newtonian limit, we did that with, we have a model with Lioche, and this is one motivation. Also, we would like to extend that to non-Markovian system. Okay. Okay, so I think it's important to see that when you're studying those problems, you're at the same time very close to experiments, but also to more exotic things. It's also important to understand if you're interested in more abstract or more foundational problems. So, I mean, the outline of my talk is I'd like to first remind you, although people have talked about that before, especially Benjamin yesterday, how do you get these continuous measurements? Then I'll explain what is the standard theory of Markovian feedback. When you feedback the result, you try to control the system just based on the last measurement results. Then I'll try to explain what is the non-Markovian extension we can do, and try to say a bit more about the evolution of the system in that case. And then I'll conclude. So just to remind you how this is one way to understand how you can get continuous measurements, is to first understand how you can get repeated measurement. So you have a system of interest in whatever finite dimensional Hilbert space, and you probe it with, say, a qubit, but it's not very sensitive to the dimension of this state. You entangle it, and then you measure the probe, which gives you, in that case, a binary result, and this binary result gives you an information about the state through the entanglement. So you have a first step, an interaction step, and then you measure. Okay, you project. So this is just putting in equation what I just said in Word. And if you repeat this step, you have a state in Hilbert space evolving doing discrete jumps, okay, after each measurement. Okay, so this is what's sometimes called a discrete quantum trajectory. So it's a fancy word for something quite simple. I have a state evolving discretely, and the corresponding measurement results delta n. Okay, that I write delta n plus or minus 1. And then if you want to get that continuous, you make the interaction soft and frequent, in which case, I mean, intuitively, this random jump process in Hilbert space become some kind of diffusion in Hilbert space. In that case, you get continuous quantum trajectory. That is a continuous evolution for the state of the system, plus an associated continuous measurement signal. Okay. And importantly, if the results are plus or minus 1, in what will be defined in the continuous limit is actually the integral, the sum of those measurement results. Because this sum of plus or minus 1 is a random walk. It will converge to an object that looks like a Brownian motion. And so the derivative of this will be the white noise, so something that is quite singular. As we will see, it poses a few problems when you're talking about Markovian feedback. Okay, so this is just to set up the stage, and then I'll spare you the derivation, but give you directly the limiting equation you get if you apply this procedure quite carefully and derive the continuum limit. So in that case, you get what's called a stochastic master equation for the state. It was already presented yesterday. So the state evolves with, of course, the Hamiltonian it had before, plus like a decoherence or dissipation term, like typical Lindblad dynamics, plus an acquisition of information term. So I think that's what Benjamin called yesterday the innovation term, which basically comes from the fact that you condition on the measurement results. In your signal is the derivative of this process, where actually it's better to consider the process directly xt, because this one is regular, but because it's this one obeys a nicely defined stochastic differential equation. So strictly speaking, the equivalent of the delta of the plus or minus 1 becomes something quite singular in the limit. So at that stage, we can also pause for a moment to notice that the history of this equation is also quite interesting. So these equations were conjectured in the 80s, and then I think in 1987 they started to take roughly the same form by people who were on the one side trying to model this continuous measurement, have a good model of continuous measurement, and on the other side people who were interested in purely foundational questions, who were just trying to modify Schrödinger's equation in a tiny way such that it collapses by itself. So it was like the collapse program, people like Philippe Pearl. I don't exactly know what was the motivation initially of Lajos in that case. It's at the beginning, the papers were mixed. So people had both fundamental motivations, but they never expected those equations to be realized in practical system as phenomenological equations. Okay, in that case, those equations are really phenomenological, but people were interested in them as fundamental equations even before it was understood they were meaningful. So this is one thing in which you see again that this field that looks quite far removed from the fundamental questions is actually quite close. Okay, so this is time to make a slight warning in that case, a bit of stochastic pedantry that will be useful a bit later. Contrary to the standard cases in physics, those equations are written in the Ito form, which is the perhaps for physicists an unusual stochastic integral defined this way. But if we forget about the definition of the integral in that case, we are going to do like physicist style, being more interested in their properties. So I assume they are defined. The two integrals are very different properties. So the Ito integral is really nice in that case because it has zero average. Okay, so when we take the expectation value of the previous stochastic differential equation, we get back the Lindblad equation. So if we average over the measurement results, it's like just not measuring them, which makes sense. However, it is not robust to smoothing. So if you start smoothing the noise, as I will need to do later to understand what happens, this form doesn't work. So you can really not smooth. If you start smoothing the noise in that case, you become close to the Stratonovich form, okay, by the von Dacai theorem. So you are not close to what you would expect. Okay, so as we'll see, you have to be quite careful, especially as the literature is full of a small misunderstanding based on this. So I mean, even many historical papers are wrong for this reason. So a few comments at that stage, because we are going to start playing with the signal. Notice that the signal in that case is a slightly singular object. Okay, you have some white noise in it. So if you plot it, okay, of course, experimentally it's at a finite bandwidth, so the white noise is not infinitely sharp, but in theory it is. And if you start doing manipulation and feeding that back in the equation, it will pose some problems, okay, because of this. We'll see that by going actually to the non-Markovian case, we'll naturally smooth the signal and have no problem. But okay, so the magic of the Ito equation is that if you average over the measurement results, if you don't consider the measurements you just did, you get back the standard master equation. Okay, so it doesn't. Nothing fancy is happening by just measuring your probes. And of course, this is a completely trivial result in this Ito form. It would be slightly non-trivial to see with the other integral. Also, a thing important to mention is that this totally coincides with stochastic filtering if the density matrices are diagonal. So you can see that as an extension of stochastic filtering. Okay, if the density matrices are just diagonal, we are simply using the Bayes rule, essentially. And this is also I think, a motivation to consider other kinds of feedbacks, because naturally in classical control, people are interested in a much wider class of feedbacks than usually in quantum mechanics. Okay, so the first step is to look at Markovian feedback, that is, feeding back this signal here, adding in the evolution a potential proportional to the signal we measure. Okay. So this is the first option. So first we can think it may look weird. So we could ask question and say, what do we want to obtain, and then build a feedback scheme that is smart given what we want to obtain. Here it's just the brute force method. You inject the signal directly, see what kind of master equation you will get, and wonder if it's interesting or not. Okay. This is like to just construct evolutions. I can do that, feeding the signal directly I can do. Let's try. Okay. So that's what you do. And this is what was done, for example, by Weismann. So there is a slight subtlety in that this stuff is divergent, so you need to be a bit more precise in how you had it in the equation. You may want to replace VDT by ADXT, but this actually gives problem even in Stratonovich form, because from some subtle reason of the commutation of operators. So this is typically the mistakes that were done at the beginning, even in the historical articles. Actually, so right now I not try to explain what really works, but you need to, actually your signal, you measure it, and so you feed it back epsilon after, or like a dt after, and so you need that your evolution plus feedback is your evolution, okay, my pointer is dying, is your evolution without feedback, and then you add the feedback potential. And of course, because of the Ito rule, because of Ito correction term, it matters to do it this way or another way. And so the quick and dirty way to derive the equation is just to start from this form, use the physicist Ito rule, and to get and you get the correct form. Later, I will give something that is probably a more robust way to get the result. So in that case, you get the stochastic master equation, which is not just the stochastic master equation you would get if you did naively put V in it. So fortunately, like the terms, the nonlinear term in the deterministic nonlinear term vanish, so you get a nice, well-behaved stochastic master equation. But let me not consider the stochastic master equation, which is what you would get if you were trying to reconstruct the state. As we are directly feeding back the signal, maybe we don't even have time to reconstruct the state. So what we are interested in is in the master equation, what happens on average. In that case, like you really have the free evolution, the decoherence or undissipation coming from the measurement. Then the feedback adds decoherence, and the feedback can also add dissipation. So this term is not like all the dissipation, but it can contain dissipation. You have two cases. Basically, if you commute, if you don't commute, feedback adds dissipation. Otherwise, feedback. Okay, maybe I assumed here that n was self-adjoint, but you can. What is important to know is that you can create dissipation with feedback. If the operator you feedback doesn't commute with the operator you measure. And the question we can ask, so now we have obtained a new master equation, a new kind of master equation by feeding back a signal. But is that, okay, what does it give us? Why is it nice? Of course, we already know it was nice because of the talks this morning. We were using that. But so to know it's nice, it's perhaps important to step back and remember what is the general form of a Lindblad equation. So you can write the most general Lindblad equation either in this form or is a non-diagonal Kosakowski's form, but they are equivalent, where A are self-adjoint. And then the question, you can see that a master equation possesses dissipation, so is in some sense interesting if, it's non-dissipative, so it's not really interesting if D is real or if all the generators are self-adjoint. Why is that the case? Because if it's non-dissipative, your evolution is exactly what you would get if you were feeding classical noise into the system. So if you just have a random potential varying in time, then you get non-dissipative equations. And so naturally, intuitively, this cannot be a resource, okay? Just pumping classical noise in the system is never something that gives interesting terms you can do computing with or whatever, okay? So this is why, so I'm just trying to give a general argument why those feedback equation you get are better than the equation you start with. So really, dissipation is a resource. This has been shown so by my boss at MPQ and many other people, that if you have master equations with dissipation, you can do quantum computing, and you can do many interesting things. But decoherence, so if you have a non-dissipative equation, these are not interesting terms in a master equation. Well, maybe it's a bit a caricature, but this is also something you have to be careful in the literature when people obtain nice new terms in a master equation and claim you are going to be able to do nice computing things with them. If they are not dissipative terms, they are not so useful, actually. But the nice thing is actually that feedback is a bit like the philosopher's stone. So if you give yourself any generic dissipative equation, then there exists a non-dissipative measurement scheme such that after feedback it gives this dissipative equation. Okay, so it's actually not so difficult. It's a lemma you can prove quite quickly. So you can, starting from a master equation corresponding that is mathematically equivalent to pure noise, but you somehow unravel it with measurements. By feeding back those results, you get basically the class of all the Markovian dissipative master equations. So this is really why it brings something. Okay, yeah, you really have that this class of equation we get by doing Markovian feedback allow us to do more than without feedback. Okay. So yeah, now we can perhaps summarize what you get by just stupidly feeding back your signal is you have something very simple and it generates tunable dissipation, so you can add dissipation with feedback. The issue is it's a bit physically unrealistic. So if you want to know what is the equation, if you start having delays, if you start smoothing your signal, because of course it cannot be of infinite intensity like the assumption we have, then we have essentially no control of that. Okay, we would like potentially to be able to describe those effects, to know what happens if, okay, I don't feedback my signal directly, but maybe I filter it first. Okay, just a first order filter is not something completely fancy to consider, but that case has actually not been considered so much, I mean, to my knowledge. And also, this is just purely mathematical. The model is quite weird to define straight from the continuum. Of course, the weirdness of these Ito processes, they vanish if you go to the discrete case. So you can always, if you are not sure what's happening in your setup, you can go back to the discrete and then make sure that the feedback you're doing makes sense, okay, in the discrete. That you have no, say, backward in time causation or stuff like that. But it's also nice to be able to work directly in the continuum, and in that case, if you are not careful, you can easily make mistakes. So it would be nicer to have some more robust approach where you can handle also non-Markovian stuff. So feedback where the signal is smoothed in a way. Okay, so this is the setup I'd like to consider. Is now, instead of adding a potential in the equation that is directly proportional to the signal, I can put something that is like a kernel convoluted with the signal. Okay, so typically you can think of something coming from a filter or okay, I mean, it can be something arbitrarily complicated, but just at least it's linear. If it's not linear, it's very hard to know what you could do. The good thing is that unless K is a Dirac, which is, if K is a Dirac distribution, you get back the Markovian case, this stuff is regular. Okay, this V has a finite value, so it makes the setup at least well-defined right from the start. In that case, the stochastic master equation, so if you condition on the measurement result, it's completely trivial. It's just what I wrote here. There is no subtlety. You just put the potential in the equation. Okay, this may look trivial, but it's not the case in the Markovian case because you have some subtleties of the infinities. In that case, you just put the potential in the equation and you can reconstruct the state. But the much harder question, and the question that is interesting, is what happens on average. And there is no way to average that stuff now because this depends on the whole history. We cannot use the fact that the Ito integral was vanishing before. Okay, in that case, we have a priori no simple way to use the same trick as before to compute the evolution for a very generic filter. So the main result I want to prove and discuss, I will discuss it before proving it actually, is that if you write the density matrix in interaction representation, you can formally eliminate the noise and write it as a time order product of, and here is the trick, of two integrals. So of the integral of this functional, which is, you see the first term corresponds to the decoherence coming from the measurement, and you have a delta showing that this doesn't have memory. The second term corresponds to non-Markovian feedback decoherence. You see the kernel K. If it were a Dirac, again, you would get back the Markovian feedback, and some non-Markovian feedback dissipation. Okay, so what I'm going to show is that you can really eliminate the noise completely to get a formula of this form. Okay, so here I'm using the super operator notations because it's slightly clearer to write the equation, so I hope it doesn't bother you too much. Okay, so that's the result I'm going to discuss. So first, we can check that if K goes to a Dirac, okay, you take the limit properly, and you get back the Markovian feedback case. So at least it's a nice way to derive the Markovian feedback straight from the continuum without running into slight subtleties of Ito calculus and stuff like that. So in that case, we start from something well-defined. We make the kernel even closer and closer to a Dirac, and we get feedback. We get the Markovian case. It's a good thing for experimentalists because it means that when you feedback the signal and it's just, it's never exactly Markovian, you have always some delay, but it shows that if it's small, you converge to the, you do converge to the Markovian master equation. Okay, so the second thing is, I am selling you something that is not so nice. So this kind of time order exponential with 2 times are super inexplicit. So the formula looks nice. Okay, I can almost trick you into thinking I have solved the problem, but actually I have not solved it much because such an object doesn't verify any nice differential equation. Yes, Jörg?
Can you tell me what this T means?
It's like time ordered, like the time order operator in quantum field theory. Yeah, there are 2 times. So you have to order the 2 times. And this is why, going to my next point, the only way you make sense of such an exponential is not through the differential equation it verifies, but through the Dyson expansion. And this is bad. I mean, this is quite inconvenient to compute things in the real world. That I am totally clear about that. But as we will see, this is also the sign that this is a hard problem and that so nothing better than that can be expected. So typically, yeah, you will have, if you would start to compute that, you will have to sum diagrams with a combinatorial complexity that will grow, and so it's not very efficient if you want to compute stuff in practice. And the only case in which it is trivial, so in which case you can immediately compute something from this formula, is if all the operators commute, in which case you are back to the classical case, which is already well understood. Okay, so the only case in which you can compute stuff exactly and quickly is when there is nothing interesting to compute. Okay, so that's a bit disappointing. But let's proceed a bit more and make a sort of aparté on Gaussian master equation. So there is an extension of the Lindblad formalism of master equation, which is in some sense the first non-trivial non-Markovian extension of Lindblad. In that case, you consider a general coupling with a bus of harmonic oscillator, or if you want, like of bosons, of free bosons. But contrary to the Lindblad case, you ask nothing about the coupling operator. Just that it is linear in the creation and annihilation, but you don't ask anything that, say, the two-point correlation function of the bus is decays very quickly, or that there is a separation of time scale. You don't ask for anything like that. In that case, using Wick theorem, you can show that the master equation takes, so essentially what you have to see is that the equation I showed before is a special case of this general Gaussian master equation. So this was written in this nice, this kind of Gaussian master equation were well known since essentially forever because it was in Feynman and Vernon. The only thing that in that case it's written in operator notation, so it's much nicer to manipulate when you have small systems. Okay, when the system that is coupled to the bus is not, say, a harmonic oscillator, when it's something with discrete degrees of freedom. And you see that this matrix is the two-point correlation function of the bus. If it becomes a Dirac, you have only one time, so it becomes a differential equation, and it's of the Lindblad form. Okay, so actually it's in Kosakowski non-diagonal form, but it's equivalent. Okay, you can rewrite that in the Lindblad form if D is a Dirac. So this is, I think, a quite important result is that it shows that our feedback equation is a special case of a generic interaction with the bosonic bus. So if you want, you have the Markovian master equation, you have the non-dissipative master equation. Our non-Markovian feedback is the yellow circle, so it's slightly bigger. And actually, you don't get everything. You don't get all the master equations. Because you only need essentially part of the decoherent that is Markovian. You can never be fully non-Markovian on the decoherence because part of the decoherence comes from the measurement, and that we have assumed to be Markovian. So this we can never remove. So that's why our yellow circle is not taking everything, but that's we have at least a large fraction. So I think it's important because it shows that we can import all the techniques that are known from open quantum system theory to linear feedback. Okay, it's not a priori obvious that linear feedback, where the measurements are really classical, can be modeled completely quantum mechanically. And so we can use the techniques that are used, like projector operator technique, time convolutionless master equation. Recently, in a few cases, it has been shown that some master equations that were thought to be not solvable are solvable. So there are a few cases where actually we can solve this. So say if you look at, for example, the spin boson model, in that case it's solvable, which means that the corresponding feedback scheme is solvable. And so if you have an exponential kernel, this is also known how to solve it. Okay, so there are a few cases when actually the equation that looked completely hopeless is solvable, and that we know it because we have mapped it to the purely open system case where people have been working on it for much more time. But I'd like to insist that in any case, you see that the difficulty is more algebraic than it is analytic. The fact that because of the non-commutation, this time order product is really non-trivial, and you just need a small non-commutativity to make this a complete mess. But having simple correlation function, except in the purely exponential case, doesn't help you much. So if you could imagine that simple filters are simpler in this setup, it doesn't seem to be the case. Like, what really matters is what operator you feedback rather than what filter you use to smooth the signal. But this is, I think, can be used in another way, is that if you look at a quantum system that is continuously measured and where you feedback the signal, this is something that is extremely easy to simulate. Okay, you can very, very easily do numerical simulation. You just evolve the stochastic master equation and you average. So you can do Monte Carlo, and you can do Monte Carlo that is super efficient in that case. The issue is like open systems, when they are generically non-Markovian, Monte Carlo is very, very hard, okay? Because essentially this has the same difficulty as QED, okay? So the difficulty in doing Monte Carlo for this is essentially the same difficulty you have. Yes, yes, Jörg.
I understand correctly the previous slide.
Yes.
You just couple your system to a bar.
Yeah.
With linear integration and then you have.
Yes.
So what's new about this? And this is sort of.
No. This is. I'm not saying it's new in any way. No, it's. The thing is, typically this is done in field theory where you have an infinite system on both sides. Okay. Here they have a nice form where you just assume matrices on the other side. So usually it's done in path integral, and in that case you have a nice time model. Okay, what they do is in this article is not just writing this. They show that they are stochastic Schrödinger equations to reproduce them. In this article is showing much more, but they write in passing. They write it this way, which is a nicer way to see the parallel with feedback. Okay, it's nicer form. But I agree, this is purely Feynman-Vernon influence, functional written in operator form. Are you satisfied? Okay, mildly. Okay, so really a point that is interesting is that now you could also think as feedback as being a tool to compute stuff. For open system, we can compute nothing, okay? Because they are efficient to simulate. So I'm trying, somehow we have mapped two problems that are difficult, and in some cases one is slightly less difficult than the other, so we can help ourselves with that. But as usual, when you map two difficult problems together, it's only a partial success because you are left with difficult problems. But at least now we know. Okay, so just briefly, the derivation. The basic idea is to go back to linear trajectories. Okay, the first steps are just a sort of formal way to go back to linear trajectories, and once you have linear trajectories, you can formally integrate the stochastic differential equation, and then you average over the noise using Wick theorem. So, I mean, I don't know if the derivation is so illuminating, but I can briefly pass through. So first you use the fact that if you take this stochastic differential equation, which is not the one we started with because it's linear, but if you solve the density matrix this way and normalize after, you get the same density matrix. So you can use this auxiliary linear equation, which is simpler to handle. Then, because I'm going to be formally integrating it, and because I don't want to use the de Leon exponential formula, I'm just going to pass it in Stratonovich form, in which case I can be a bit careless with differential calculus. So once it's in Stratonovich form, I just use the standard ways to pass from Ito to Stratonovich. In that case, I just have a linear equation, so I can formally write it as a time-ordered exponential. If you are not so comfortable with time-ordered exponential of stochastic integrals, you can always give meaning to this expression with the Wang-Zagai theorem. So you first smooth the noise, make it an ordinary differential equation, an ordinary integral, and then take the limit of delta correlator for the noise to make sense of it. Okay. But you see that now you have the time order exponential of something linear in the signal. Okay, it's true, it is integrated, but it is a linear version of the signal. So it would be possible to integrate it if the signal were Gaussian, but the signal is not Gaussian, depends on the state. Fortunately, something we could have also seen quite easily in the discrete, we want to compute the average of rho. And the average of rho is not the average of this rho linear. We have to multiply by trace. This makes you want to redefine the probability measure to include this row in the measure, okay? And via Girzanov theorem, you realize that xt is Gaussian for this measure. So xt is not Gaussian for the physical measure, but it's Gaussian for this modified measure. So if you want, it's a bit, I think the word used, Wiseman is like you have a difference between the physical distribution and the ostensible distribution. I'm really going from the physical to an auxiliary distribution in which the computations are simpler. So what I can do, instead of averaging this, which is difficult, I average rho L with this measure, and this gives me the same rho. The only thing in that case, in one case, I'm averaging something nonlinear with a nasty measure. In the other case, I'm averaging something linear with a Gaussian measure. And then what you do is then once you have an exponential of something linear in a Gaussian variable, you just use Wick theorem, or in the classical case, sometimes it's called Isserlis theorem to, sorry?
What is Isserlis theorem?
I think, so what I understand of Isserlis is when you use Wick theorem for classical probability, for Gaussian processes, but in the classical sense, you should say Isserlis, but this is purely semantics. Wick theorem is perfectly fine. And then you get back the formula before. Okay, like this is just like the cross product of the. You can really see that as the correlation function of the signal we have fed back into the system. Okay, so we are back to our result, and you see that the derivation maybe looks slightly complicated in the continuum, but again, it's all the steps are rather intuitive if you have the discrete picture in mind. So, yeah, I guess at that point, so I'm slightly early, but then I guess you'll have time for questions or more time for coffee. We can summarize. So I think, so the first thing is to understand why Markovian feedback is nice, why we would even do such a thing in the first place. So it's nice because it can add dissipation to equation, and dissipation is a nice resource. Okay. Non-Markovian feedback can be solved formally, as I showed, and it has the same structure as general open system evolution. So we map two complicated problems, but at least we know they share the same structure, and so the same techniques we can use in both cases. There are many interesting things we could try in this context. There are many non-Markovianity measures on the market. So methods that try to tell you whether the bus you are interacting with is non-Markovian or Markovian. There are many candidates for measures of this, and sometimes called quantum non-Markovianity. The question would be to see if this kind of feedback is considered non-Markovian for those measures, or is it strongly non-Markovian with those measures, in which case you could not really argue that these measures are measuring quantum non-Markovianity, because I'm really adding this non-Markovianity in a purely classical way. The nice thing would be to try to estimate stationary states. This is really what we are interested in the end. What kind of states are stationary with these feedback schemes? But this is not entirely trivial, actually, with the formula we have. Of course, again, you can Dyson expand, so get series expansions of how your stationary state looks like, but this is clearly something we'd like to do better. I went non-Markovian for the feedback scheme, but my measurement stays Markovian. I think the thing no one and people have been trying to do for at least 20 years is to try to find a good notion of what it means to non-Markovianly measure, to have memory in the measurement process itself. So our stochastic master equation is driven by an Ito process, by something that is very Markovian. But would it be possible that it is driven by colored noise? Okay, that is something people have tried to construct. There are known equations like that. So there are stochastic Schrödinger equations with colored noise, but it is known, it has been proved that they never correspond to a measurement scheme. So they are pure mathematical tools, pure unravelings, but they have they don't correspond to a concrete setup of measurement. I'm not even saying concrete in the physical sense. Even mathematically, there exists no measurement model giving rise to such stochastic Schrödinger equation. So in the discrete, you can try to do that with probes in a matrix product state, but this is we have no better idea, something we have been exploring, discussing with people here, with Clément, for example, but it's very unclear what you would, underneath, sorry, that we would do in that case. So yeah, I think that's all for today.
Questions?
Do you have checked what kind of problem from interaction with a bath, linear interaction with a bath, that you can plug into a Markovian feedback scheme? Something that you can solve.
Yeah, no,
From
I mean,
bath culture to feedback.
so you
What
need.
kind of feedback it produces?
Yeah, the issue is
No.
this is quite so far. This is what we have managed is quite restrictive because we need that at least for some operators of the bath there is a delta correlated part. Otherwise, we never get the Markovian measurement part in the equation.
Okay.
Then you can wonder yeah, but what if we don't care? What if we remove this delta by hand? Okay, in that case, just for numerics. In that case, you break positivity, so your phases explode. Okay, so once you average, it's fine, but in your simulation, you have the typical trajectories you get have exploding phases. So it's. I mean, if I don't have the killer application right now of this.
Okay. And so you speak on estimation of stationary state, but you have also a notion of closed loop stability.
Yeah. No, that I have not.
Something because, for example, if you take a first order filter, exponential decay for the kernel that you use for the feedback scheme, then in this case you have a first order differential equation. So you can just write a stochastic differential equation where the state is the Cartesian product of the state of your first order system, okay? And then you have a Cartesian product with the state rho, okay? You have sort of something like this. So you have a stochastic equation, which is not a stochastic master equation, okay? But it is still you have a state. So this is a stochastic differential equation, but it is a nonlinear one.
Well, I mean, this is as I said, I tried the brutal way, which is you just plug everything, see what you get. What you are considering is more if we were smart and have an idea of what we want to get, and see then in which cases the feedback is stable or anything like that. But so far I have not studied anything that is. But I agree that this is interesting. But you have to remember also that I'm partially motivated in just to see what kind of equation in general we get. Also because it's interesting for these other foundational questions where we want to know what kind of equation we can generate with such methods.
Just a naive question. Did you mean that it's not completely quantic, your resolution, it's semi-classical? At the end you said something that puzzled me.
About what?
Well,
sorry,
you
I
said
forgot.
I don't remember what you said exactly, but I heard that it's not completely quantic resolution. Maybe I missed it.
No, I mean, my point was that if you look at a feedback setup with a controller on a quantum system, this is clearly the extreme case in which you have something that is classical and something that is quantum. Okay, like your controller is classical. It's a chip in a computer. You could even imagine that it's some guy who is reacting to. Okay, so this is really clear.
I understand. In the sense of your first scheme at the beginning of the.
Yeah, exactly. But this is very nice because actually coupling classical and quantum variable is something non-trivial. To do it in a without having absurd things. Okay, so feedback schemes are really nice for that because and then you forget about feedback. You forget about how you obtain the equation. You just know that by design, because their structure is going to work because of the way you constructed them.
Do you try to introduce memory inside the noise? For example, to change the Brownian motion with another noise with memory, like
you
fractional Brownian motion or
for
something like
for the measurement part.
Yes.
Yeah. So for the measurement part, as I said, no one knows of an equation that represents something physical. Okay, but then we can. So what we did with Lajos and Luca Ferialdi is just you take those stochastic Schrödinger equation with colored noise. So it's not fractional Brownian; it's like colored noise. Just say exponentially decaying kernel. And you do feedback as if the signal were some real thing, even though there are no-go theorems saying that this can never be the signal of any measurement schemes. And in that case, you can show that what you obtain, starting from a non-dissipative general master equation, non-Markovian, you can get all the non-Markovian dissipative master equations. So you get the same kind of theorem, although everything we do doesn't represent anything physical. So you can play this formal game, but the problem is that right now this game is super formal because these models are just, if you want, generalizations, but that have nothing, that cannot be implemented. And this is why I think this going back slowly to the discrete case of entangled probes is something in which case you would be able to say stuff, and that is manifestly something you can realize. As we have discussed, the problem in that case is not clear how to scale it to get something non-trivial remaining in the limit and not be absorbed by the Markovian case.
I have one small question as well. So if you implement your non-Markovian feedback on the simplest measurement equations that you can imagine, so there is no evolution, nothing, just non-devolution measurement, let's say, and you use then the measurement to include in your to put a Hamiltonian in your system. So is there any hope to solve, or is there any interest in doing that?
I think this is if everything stays diagonal, it's completely all right. So so you would want to put a Hamiltonian that does not commute with the measure, otherwise it would be completely trivial. And though in that case, I think it's already hard. Like it's already a hard problem, because when you think you can look at if you start doing the Dyson expansions, you will have tons of commutators that will never simplify. And the interesting thing with this is that there is a completely trivial case, and there is no first non-trivial interesting case that you can solve analytically. That's a bit the frustrating part, I guess. Yeah.
The way you describe feedback is the same thing as open quantum work.
Yeah.
Okay. Like just a comment. I was just saying that the way you define feedback is the same thing as open quantum work, where you move what you call in open quantum work, you are on the lattice, and you move depending on the measurement you do. So it's exactly the same thing as what you do when you do feedback.
Yeah.
So maybe you can use techniques from open quantum work to study your problem.
So if you look at a standard homogeneous open quantum work on okay, no, or on say on 2D, not on an abstract graph. Okay, in that case, the natural thing you feedback is not really what I called ST, but rather XT. So what you feedback is the integral of the signal. So you have to see what you get in that case. But maybe with non-uniformity you can get something. But this is, at least it doesn't give the Markovian feedback case. It is, I think. Okay, we can talk later, I guess.
Okay, let's thank Antoine again.